All right, let's, somehow the volume is just high by default now. Okay, so I want to start the next sort of module, if you will, in the class. We're going to start talking about stochastic control, robust control. RL kind of fits into this part of the picture, okay? But to kick that off, I want to first talk just about dynamics. Today we're going to just talk about dynamics, but we're going to start sticking in probability into our dynamics, okay? So I think it's actually been interesting over the years as machine learning has become more pervasive. I think a lot more people are a lot more comfortable with throwing probabilities around, at least using the language of probability. But I think you can talk about log probabilities, maximum entropy, whatever, but still maybe not have thought through some of the implications of putting probability into an equation, a differential equation, and see sort of what that can do. And my goal for today is to just give you some intuition first and some of the mathematical tools around reasoning about stochastic differential equations. And that will then follow up with like, how do we control those things, okay? So there's a bunch of different notations I could pick, but I'm going to try to stay close to what we've been writing throughout. And that actually, it turns out to be the right way to do it in software too, okay? So, so far we've been mostly working with, let me say, maybe so far we've been doing differential equations that look like this, okay? And difference equations that look like this, okay? And then today we're going to make only a super modest change. It's like notationally it's almost nothing, okay? I'm still going to use the differential equation form, okay? But I'm going to throw in a new input, W, okay? WT or WN is a random process. Is the output of a random process. So it's a vector. It's a random vector. The outcome of a random process. And we'll define that in a couple of precise ways today. But basically, think about every time I go to evaluate f, there's going to be some of my inputs that are going to be, let's say, drawn from a random number generator, okay? But having quarantined, if you will, the randomness to my inputs, I can still work with the deterministic form of the dynamics. Right? I can still write f of xu using my differential equation know-how, and all of the interesting stuff is coming in through that random input. Well, there's other places it can come. Interesting things can come in, but that's the idea. Stick with differential equation form and use the random inputs. Now, this is actually an extremely general form, right? So, well, first, I guess maybe W can model a bunch of things. This is like a super general form, right? So it can model disturbances, if you will. Maybe you're a UAV that's flying in the wind, and you want the wind to be coming in as some sort of a random process. You could use W to seed the perturbations that are coming that describe the wind, right? It can model. Let's say, parameter uncertainty, if you will. Right? If you don't know the mass of your quadrotor or your biped, okay, you can put it in like that. Maybe that one is constant over time, the effect of that, but it certainly fits into this this form if you want. Okay. It can be domain randomization if you're doing RL and you want to somehow say the environment is drawn from some distribution, right? Maybe the terrain is drawn from a distribution, right? That can be modeled by being captured as the parameters of W, right? Maybe the step height comes in through W, and that changes the equations, right? But this is a very general thing, because once you take even a simple random number generator and then put it into an arbitrary nonlinear equation, then you can get arbitrary rich things coming out. So that's not limiting at all, really. The only thing that we're not modeling yet, a lot of times when you start talking about stochasticity in robots, okay, you start thinking about both sort of the dynamics, the effect that it has on state, but also the effect it has on your measurements, right? So measurement noise, like sensor noise, is a thing, but that's not immediately captured in this. This is, sometimes people distinguish between process noise, the things that are affecting your state dynamics, versus measurement noise. And we'll talk about measurement noise when we get to them, when we think about output feedback and pixels to torques kind of things, okay? But today the focus is on the way these disturbances come in to affect your state dynamics. So that's the process noise version of this, okay? And oftentimes, not exclusively, we'll oftentimes see even a specific version of this, which would be additive noise. If I just separate that out and say that Wn actually introduces itself in an additive form, that tends to be a nice thing to analyze, and it actually tends to also not be super limiting, because in one step it only adds to xn, but then xn gets fed back in here and then becomes arbitrarily interesting and rich on the next step. Okay, so that can still be a very rich model, but it'll be a little bit more convenient for some of our analysis. Okay, now you can do everything in continuous time or discrete time. I tend to hang out in the discrete time for today's lecture because it's just a little bit easier with the notation to think about discrete time processes, where at step n, you're going to draw from a random number generator. If you think about a continuous time random process, that's all perfectly possible to define, but it just takes a little bit more rigor to get that right. So we'll mostly stick in sort of these versions of the equations today. Okay, so let me start with some really simple warm-up examples, just to get the tools flowing. I guess the simplest I could possibly do is if I think about sort of a linear system. I'll do the discrete time version of this in a second, but let's just start with the continuous version of this dynamics. Then this is a flow on the line. It's a linear flow on the line. I'll even say that alpha is greater than 0, okay? So if I just draw x versus x dot, then we know that this has a dynamics like this, right? And if we remember our beginning lecture kind of thing, I said if x dot is above the line, it's moving this way. Below the line, it's going this way. So that means it's got a stable fixed point at the origin, right? Simple linear systems. That's just the graphical version of it. I find for thinking about flows of probabilities, you can certainly think about it this way, but maybe it's a little bit helpful to think about this as the motion of I want to think of it as a potential flow is what we'd call it. I'm going to write the exact same equations, but I'm going to write it slightly differently. I want to think about this as, let me define a potential function, okay? All right, and then I'll think about the flow of this as being x dot is basically going downhill on the potential, right? Which is exactly the same thing, negative alpha x. So just intuitively, right, this dynamics, you could kind of think of it as like a particle living in a bowl, doing gradient descent on the bowl, just kind of rolling down to the bottom of the bowl. I think conceptually, since we're going to have lots of particles moving around in a second, having a sort of physical intuition about that equation, thinking of it going down the hill on a bowl, I think maybe be useful. Okay, so this is, you could just say this is like the potential function version of that. It could be a Lyapunov function too, of course, but just a general, sometimes people call this gradient flow or potential flow. It's a perfectly valid way to describe dynamics. Okay, and then if we want to make a discrete time approximation of that, then I'll end up with something like xn plus 1 is xn plus some just time step times f of xn, right? It's kind of my discrete time dynamics, and I'll just make that simple by choosing h as 1 and say it's that'd be my sort of discrete time approximation. Okay, and now let's go ahead and add noise into our discrete time approximation. So we're going to now say xn plus 1 is xn minus alpha xn plus additive Gaussian, or additive noise. And I'll say something about this, but let's say this is drawn from some Gaussian. Okay, that's saying that at time n, I'm going to draw from some normal distribution with mean 0 and variance sigma squared. Okay. Would be a perfectly reasonable sort of way to do that. And if I additionally make sure, if I impose that, so mean 0 means the expected value for xn equals 0. That's just the mean 0. And I can additionally call this an IID process. Okay, IID. If I say that the noise at step n and the noise at step m sigma squared if n equals m and 0 otherwise. If there's the covariance, if there's no covariance between these at different time steps. This is a way to call them independently identically distributed. Basically, I'm going to flip the coin every time step, as if I had never flipped the coin before. Yes? Oh, I should have written W here. Thank you. Good catch. That was meant to be a W. All right. Please feel free to ask any questions about notation. But I'm not going to lean too heavily on it. I'm going to mostly use basics like this. Okay, but if anything I read is unclear, please ask. So now the question is, what's the right way to think about this dynamical system, right? So all of our basic questions are still in play, right? So is x equals 0 a fixed point? Is the system stable to that fixed point, right? These are all very reasonable questions. I saw at least one person answer. I think the answer is no for both of those questions. Right? The picture I'd like you to have in your head is that this thing is going downhill, but it's bouncing around a little bit. And even if it gets to the bottom, it's going to be bouncing around a little bit. Right? There's definitely a forcing term that's bringing it down towards the origin. Okay? But there's a random noise component that gives it kind of a Brownian motion. That's what the biologists would call it. You know, Brownian motion of this thing's bouncing around. It's always got the jitters. It's never going to sit still. Okay? So even if you put it directly at the origin, it's not going to stay there. It can bounce around. So I think the notion of stability, it's kind of just the wrong question, right? Now, even though the randomness came in through W, because it affects x at time n, for instance, is now a random variable also. Okay? So you can ask about the mean of x. You can ask about the total distribution of x. Okay? But asking about x as the way with our deterministic questions is no longer the right thing. Okay, so what we need to do is sort of transition to thinking about a probability distribution over x more generally. I'm going to write it as the probability distribution over x, the probability density function, okay, at time step n. This is the probability density over x at time step n. Okay? And we want to think about that probability density. And the picture, again, that you should have in your head is that even if I started it here, it's just going to, the random variable is going to jump around. Okay? But it's going to be interesting now to think about what the probability distribution does. So let's do it on I'll make some animations here to make it clear. Let's do the slightly more interesting example. So if I did my cubic polynomial that I love, right? I'll do this version of it. Do x minus x cubed, which is this version. Okay, so it's got 3 fixed points. This is x, which is x dot. Oops. X versus x dot. Since it's like this, we know that this is a stable fixed point, and this is a stable fixed point. Okay? I'm going to make the discrete time approximation of that. Okay? And I'm going to simulate it. So I can think about this thing as a potential flow. Right? So this thing is like a potential is -1/2 x squared plus 1/4 x to the 4th. If you plot that, it looks like this. This goes exactly to 0. Right? This is u of x. This is -1. 1. So that's what you expect it to do, right? If I put a particle here, it's going to roll down to, I'm sorry, this is -1. This fixed point here. This is -1. Not that one. And 1. Right? It's going to roll down to this fixed point, which is corresponding to converging here. But what I want to do is somehow lift us from thinking about the single point. Oh, sorry, go ahead, yeah. Well, I use the potential function as saying I'm going to go downhill on the potential. So there's a minus sign there, yeah. So I'm going to use this potential function, and I'm going to add in W and do the discrete time approximation. And what's going to happen, right? I'm going to get rollouts of things that go here, but bounce around a little bit. Rollouts of things that go here, bounce around a little bit. If I'm here, probably I'm going to go here. Okay, but it actually gets more interesting than that. You'll get particles that will, with some small probability, eventually make escape attempts and jump over to this other side, okay, and jump back. And if you play any one rollout, it can actually be very rich and complicated, right? For even a long-term simulation, it might not only stay around the vicinity of this, it might actually go to another one and back. Okay, so I think what we have to do is shift our thinking from thinking about the rollout of any one thing to actually what is the evolution of the probability distribution over initial conditions. And I made a little animation here. Okay, so this is going to be, I'm going to simulate many particles moving down this function, okay, moving on this function. And I'm just going to plot the histogram on top of the function, okay? This is what happens. Okay, that's kind of what you'd expect, right? If I started with a delta function, all of my particles sitting exactly at the origin there, then they're, with a little bit of noise, they're going to pick one side or the other with roughly equal probability, and they'll sort of slide down. And then there is going to be occasional escape attempts where particles from here will jump over there, but with sort of equal probability, they'll jump back over here. Okay. Now here's the amazing thing. Even though the path of any one particle is complicated, right? Doesn't have any notion of a fixed point or whatever, this plot will reach a fixed point and stay there, okay? Even though the points won't converge, x doesn't converge, probability over x does converge. The density function does converge. So we need to lift our thinking about fixed points of the state to fixed points of the probability distribution. Stability of the probability distribution, okay? So the dynamics of the probability distribution are going to be sort of simple enough, right? So we're going to write P of n plus 1 of x. In general, it'll be over, continue with all the real values. This would be the probabilistic form of it, okay? I've got some dynamics here, which I'll show you how to go from this form versus the f of x, u, and w. It's just another way to write that. I can write the probability distribution of next x's conditioned on a particular x, okay? And this is now a function, a map that goes from, if I know the probability distribution at n, I can map it to the probability distribution at x at n plus 1. I've got a function here that maps to a new function here. And I want to think about the dynamics of that function. Yeah?
So x prime was your
Yep. I just need two variables. Oh, this should be over x prime. I missed a prime there. Yeah? Yep. Yeah, thank you. The probability of me being at some particular location here is the, from all possible previous locations, the probability of being at that previous location times the probability of me getting to this new location from that previous location, right? So the dynamics of this is like the probabilistic dynamics. Sometimes it's called the master equation. That's probably not PC anymore. No, GitHub changed master branch to main branch, so probably that has to change too. But it's sometimes called continuous state Markov process. It's related to a lot of things you might have heard: Barone-Frobenius, Fokker-Planck, all these different equations. This is the simple version of it. I would just call a continuous state Markov process. Okay, so I want to play with this a little bit today with a couple other examples, right? So actually, more generally, so I emphasized W here being a random noise that's generated on every sample. But nonlinear dynamics are awesome, okay? And complicated, rich, beautiful things happen with simpler inputs, right? So it turns out even if you have a deterministic dynamics, but you have uncertain initial conditions, then you can already get beautiful probability distributions flying around, okay? So I'd say in general, there's a bunch of different, like even in code and in our math, there's a couple different ways that we tend to list the sources of uncertainty here. Even in Drake, this is how the code is laid out, okay? We identify a handful of different, it's like the general form of the dynamical equations that you can write as a leaf system in Drake. You also have the ability to specify parameters. Okay, you can say like the mass is a parameter, for instance, in your dynamical system. So you can write, in general, of course, you can write a probability distribution over W. That would be the random inputs. That's the one I emphasized before. But you can also get randomness from just having the probability distribution come in through the initial conditions. The other one that's sort of clean for analysis is you can have a probability distribution over parameters. Again, if I didn't introduce this notation, I could have just made W a boring random process to capture the parameter variation. But it's sort of interesting in code that we've been able to write all the things we wanted to write in Drake by just calling out these three specific types with sort of one more catch-all, which is just something that draws your whole dynamics from a random thing. So for instance, if you have, if you're doing domain randomization and you want to initialize your robot with a random number of objects, okay, then the size of the vector x changes on every draw, right? So that doesn't fit neatly into our state space equations here, right? But you still want to be able to analyze that, okay? So there's sort of a higher class of just, I'm going to say every time I pull on the random number generator, I get a new simulator out, basically. And those are all sort of really worked into the code in Drake, which is not coming up right here. Okay. So that example of sort of the cubic polynomial was a way to play with random inputs. Let me show you how random initial conditions actually can already, just by themselves, do some cool things. And there's this classic, beautiful example from chaos theory. Okay, you take a chaotic dynamical system that's deterministic but just crazy, and you give it random initial conditions, and you get the same sort of beautiful distributions flying through. Okay, so here's another example. Logistic map, tent map. People know this for various different names. Okay, the equations are simple. famous one, okay? It's defined over the interval 0 to 1, okay? And if I plot xn plus 1 as a function of xn, then it just looks like a tent, roughly. That's not quite as symmetric as I was going for, but this is my dynamics. Okay, and if you remember sort of how we played with the same kind of flows on a dynamical system, this time you can play with, you can get intuition about a discrete time system by thinking about how it intersects with the line of slope 1. So there's a fixed point here, there's a fixed point here. But are those fixed points stable? Well, that's complicated. Because what happens is even if you have a deterministic initial condition, the way you play with this, if you wanted to think about how is this going to evolve in time, you can simulate it with these little tricks like this. So I'm going to say, well, xn plus 1, or xn this would take me to this xn plus 1. If I want to bring that back to xn and iterate again, it's similar to just projecting it to the line of slope 1, and then going up to the map again, here, 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 here. You could just start doing crazy things, okay? I don't know, it'll jump all over the place, okay? This is a chaotic system. Small changes in initial conditions could lead to very different rollouts. And it's just one of the famous simple ones. It turns out, if you take that system and plot any one rollout, it's going to be crazy, okay? But if you instead say the initial conditions are drawn as a uniform probability 1 over the interval 0 to 1, that's the initial distribution, P0 of x. How does that distribution, P0 of x, evolve? Okay. After one step, the probability distribution looks like this. After 2 steps, it looks like this. And after 3 steps, it converges quickly to a steady state distribution, which is this dashed line here. That's kind of P infinity. And it will stay there forever. Okay. Individual rollouts of this system are chaotic. They're crazy. The probability distributions are beautiful and simple and clean. Okay. Every time I think of this, I think of Isaac Asimov. You guys know Isaac Asimov? I mean, okay, but have you read the Foundation series? Like, do you know what the reference I'm making here is? The Foundation series was about psychohistory, right? And the basic premise was that humans are complicated, right? Every individual is very hard to predict, okay? But the statistics apply to large groups of people. So once humanity got to a certain scale and we're covering the universe, then actually it became predictable again, right? And so Harry Seldon predicted what was going to happen far out, and robots were involved, okay? And so he was guiding humanity through devastating situations, and by playing with the law of large numbers and saying that even though humans are individually complicated, the total effect is predictable. That's kind of what you see in the logistic map, right? You can see in very simple dynamical systems, any one rollout is bad, but the probability distributions are beautiful.
Go back to the plot.
Yeah.
Those are just the evolution of the distribution over time. It's not it's not converging for the initial time. It's always saying that uniform distribution, and then
At time, so the way I'm going to say it is that at time 0, if I were to just roll this out once, I'm going to pick from this distribution, right? At time 1, it'll be like a sample from this distribution. At time 2, it'll be a sample from this distribution, yeah? So that blue line is the total probability distribution, like the histogram of particles that I would plot from time 0. If it's initialized with particles evenly distributed, then on the next time, the particles will be distributed like this, and on the next time, the particles will be distributed like this.
there's no sort of concept of convergence of these blue distributions for that. That fully specifies the
Yep, this is the blue line is P, it's in my notation, it's P subscript 2, so that's n equals 2. The distribution is a function of x. And if I keep iterating this map, then it converges to P infinity, which is the orange dashed line. So it does converge, and actually quickly, to this steady state solution, which is the dashed line.
So there's two convergences happening here, right? Like one is through, as you're evolving the dynamics, you're saying you converge to the orange, the P infinity. But if I start picking different initial conditions and running it to only the time 2, does that also?
That's going to be crazy. So if you take any one initial condition, then there's no notion of convergence or stability there. It's going to bounce around forever, right? Any one particle is doing crazy things, but in mass, it's doing simple things. Just like the two wells where some particles are making escape attempts, but on average, they sit comfortably in balance. Yeah. Yes. I did. Yeah. Nope. You could start them anywhere. The picture, if I started a Gaussian here, they would kind of go down and converge to a distribution here, right? So that the cubic polynomial specifically, if I had started that, okay, let's ask that question. So in this example, if we started the delta function over here, what would we expect it to do? So I would expect, and I think we could prove this, would be that you'd come down and you'd get a lot of probability mass here and almost no probability mass here. But you'd have very slow leaking, and that eventually it would actually, if you looked and came back a long time in the future, it would actually look like this again. I think it would be a long living distribution over here, but it would eventually leak over and find its I think this is the only stationary distribution. Yes?
When you say the probability distributions converge, in what sense?
That's a good question. So I think probably most functional analysis tools would, in most senses, they would probably converge. I think point-wise, yeah. I think by most norms, I would think it would probably, all of them are well behaved in that sense. But certainly for these examples, yeah.
The next slide.
Harry Seldon? No? That's a good question. So what's happening at the fixed point? So the fixed point is not moving, but it's also not special. There's infinitely close to the fixed point. There's you're going to bounce away, right? If it was a stable fixed point, you'd expect a, yeah, absolutely, yeah, yeah. Yeah. I think you can analyze those algorithms with as a random process and ask about its stationary distribution, its mixing time, all these questions that you would use in the tools from Metropolis Hastings and Monte Carlo MCMC kind of algorithms can run through this kind of a analysis. Absolutely, yeah. You can have multiple fixed points, just like you have multiple fixed points in nonlinear dynamics. You could have multiple stationary distributions. Yeah. I think the analogy to nonlinear dynamics is actually strong, right? So you could have you could have a region of attraction in probability space to some stationary distribution. I mean, oftentimes, if you have things that are ergodic, right, things will mix, and it's very common for systems to have a unique stationary distribution, but it's certainly possible to have multiple stationary distributions. As soon as they kind of mix it all, then you tend to have something that will eventually converge to a single stationary distribution. under weak assumptions, you will get a unique stationary distribution. Great questions, yeah. Okay, let me, I think actually it's worth just working out a little bit more carefully here, just what happens, I think, in the linear Gaussian case here. So let's just say, because it answers a lot of these questions nicely, formally here. Okay, so you can do the matrix case, of course, but I'll just keep it simple and do the scalar case. And I'll say that W is IID Gaussian. Okay, which basically just means, if I use the notation here, that means that my density function is just my standard Gaussian. Which I'm just calling okay, so if I want to think about how do I take a probability distribution on x at some n and propagate it to the x at n plus 1. And my dynamics are simple like this, okay? But even though I've written this as a dynamical system in ODE form, I can translate its dynamics into the conditional probability form. Right? And it turns out, because probability of xn plus 1 as a function of xn is just, well, it works out to be this. Let me write it this way. Alpha, I call it A here. A xn sigma squared. If I say mu is 0. Let me just say that in words here, okay? So if I'm conditioned on, if I know where xn is, and I want to know where xn plus 1 is, okay, then because the randomness comes in through w here, right, in the one-step case, then all I'm going to get here is another Gaussian, right, which has a mean at axn. This one is just the mean, right? And then my same Gaussian just now centered at axn. And then if I go to do the convolution of this x conditioned on x prime times p of n x prime dx prime, there's a few important cases where I can take the integral of a Gaussian with another Gaussian and everything's clean. Okay, there's basically two cases. That's really nice. One is two Gaussians stay Gaussian, right? And the other one is if I have a delta function here, then I get a Gaussian out. This is like, if you remember, you've taken a signals and systems class and you've done convolutions, right? So if you convolve two Gaussians together, you get a Gaussian out. If you convolve a Gaussian with a step, you get a Gaussian out. Okay. So if I choose P0 of x to be some Gaussian with some initial condition and some initial covariance, I'll even make it even simple. I'll keep it 0 to begin with, okay? Let's think about how that evolves. If I have that, then I get P1 of x is another Gaussian, okay? Still with mean 0. And you get the sigma, I'll call it sigma W, keep it super clean, plus sigma 0, A times sigma 0 squared. That's just the, when you convolve two Gaussians together, you get a new Gaussian with its covariant, with a mixture of covariances like this. And what's awesome is that if you keep iterating that, then you can solve for the stationary distribution of this. Basically, you get sigma n plus 1 squared is going to always be sigma w squared plus a sigma n squared. And you can find fixed points of that equation. The steady state distribution here looks like this. Okay. What have I just said? So if I have my potential function on this linear system like this, and the curve here, this is 1/2 ax squared, okay? This is well behaved when a is between, well, for the discrete time system, it's, this is well behaved. When a is between -1 and 1, which is exactly when the discrete time system is stable. A discrete time system, right, has a stable fixed point if the linear dynamics, if a is between -1 and 1, right? Because the long-term dynamics here are x of n equals 1, sorry, equals a to the n x of 0. So if a is greater than 1 or less than -1, it's going to blow up. But if it's between -1 and 1, it's stable. Okay. So as long as I'm in this regime, then this denominator is well behaved. Okay. And I get a steady state distribution, which is what? It's two things. It's the noise that's pushing me out, right? So I've got sort of noise pushing me out. There's one force here, which is sort of being pushed out by sigma w squared. And I've got another thing that's making me smaller, right? If a is closer to 0, then that's kind of pushing me in. So if I make this sharper and sharper, then I'm going to get a sharper and sharper stationary distribution. If I make this a weaker stability, then I'm going to get a broader distribution. Okay, but they come into balance. So I think the linear system is sort of simple enough that you can see there's this balance between stability in a deterministic sense and randomness in a stochastic sense. Right, that will shape your final feedback stability, your final stationary distribution. And similarly, if I were to do the same thing with mean not 0, then we would see that the mean just converges like the deterministic system. This just the mean will converge with alpha n, okay? But the covariance will go with this rule. All right, there's one more super quirky thing that even with these simple examples that I want you to see. Let me do the cubic polynomial again, but I'll do the flipped version of it. Okay, so let's do the deterministic version of -x plus x cubed. Okay, so I did that one before, now I'll do this one. x dot, I'm going to do the deterministic version. So this time I have an unstable fixed point here, a stable fixed point at the origin. Okay. If I were to do the same thing now and start a lump of probability at the origin, then what's going to happen? What's the stationary distribution of this process? Yeah. Okay. So I'm going to get a, let's say I started with, after one step, I've got a Gaussian, okay, and I've got stability that's sort of pushing it in. So I've got something, I mean, locally at least, it looks like the linear Gaussian thing. So I'm going to get something like what we just did, okay, around the origin. But you kind of expect it to maybe take escape attempts. So I always hear like, you know, when you don't tie the hot air balloon or the balloon at the party well enough, and you kind of hear the, you know. So the probability distribution of this, it doesn't have a stationary distribution, right? So you start with a nice, beautiful Gaussian, but the longer you watch, the more probability mass you lose, because as soon as it, you know, any escape attempt that sort of hops over here is now going to run off to infinity, right? It's very unlikely that it's going to come back. It could, right? So this thing, you know, because those things are just constantly running off unstable, we would say it doesn't have a stationary distribution. Yeah.
Does it have a stationary with respect to the original distribution you dropped in there? Is there some dependency there?
Tell me again. So you say it's stationary with respect to the initial.
With respect to the fact that you dropped the delta function to begin with?
Yeah.
Is it like a function of like if you have a uniform distribution to drop in?
I think any distribution I drop in initially will eventually, because I've got Gaussian noise, which has infinite support. Basically, there's, you know, always, no matter what the distribution is to begin with, it will always have some particles that are running off, and then once they're off, they're kind of gone. Yeah, so I think that's a robust thing for any initial condition. Yeah. Yeah, I mean, this is not a chaotic system, right? The deterministic version of this is beautiful and simple, right? So I wouldn't call this chaos. I'd call it, you know, I'd call it wrong to ask about the stability of fixed points for the stochastic system, right? I mean, this is real. Okay, let's be philosophical for a second. Like every robot we've ever built is like this, right? I mean, it's kind of sad, but like your autonomous car will eventually crash, right? Like at some point, somebody's going to drive a truck that has like a painting of a highway in front of you or something, you know? Like it's low probability, but it's going to happen eventually, right? Every walking robot you'll ever build will eventually like be walking across the street and get hit by that Mack truck, right? So if you haven't got this working in your dynamics, then you haven't fully captured what happens in the world, I think, right? So this is probably a more accurate depiction of what's happening in reality. Yeah. It's the heat death of the universe, something like that. Yeah. Yeah. That sounds grim. And I was just talking about robots, you know, but no, I hear, yeah, that's like entropy, right? So I'm with you. Now the question is, so this does do something meaningful before it dies, okay? And that can be, if that lasts for a long time, like diamonds are metastable, right? They will eventually turn back into coal or whatever, you know, but they're going to be pretty for a long time, and that's useful to think about. And robots will tend to walk for a long time before they fall down, and so that's useful to think about. But if we're in the land of probabilities, then we have to be mindful of the fact that most equations we write down could actually fail with probability 1. Yeah, what might be?
If you run this to infinity, will it just go into two distributions where the asymptotes are? Like graph? Or yes or no?
This one's technically running to infinity.
There's no asymptotes.
Yeah, yeah. Just spreading out to infinity. Yeah.
Will all the points be on the left and the right side eventually?
That would depend on initial conditions, right? So, yep. So I think given that they were sampled uniformly, you'd expect even probability at, you know, towards racing towards positive infinity and negative infinity. Yeah, I think that's true. It's symmetric. There's no symmetry breaking here. Yes.
In the real case, so the problem here is that at either end there is something unstable.
Yes,
For the robot, it's bounded.
that's true.
So how would this probability distribution, would it become something uniform or something if it was actually bounded at either end?
So a lot of times, that's a great question. So the question is, real robots are bounded. They can't go to infinity, right? Velocities don't go to infinity quite. They can get pretty high if you mess things up. But so I think oftentimes we'll say there is some failure state, some absorbing state. Maybe it's like an accumulation of every robot state that involves your robot being on the floor broken, right? And so we would say that there's a transition when your robot hits the ground into this absorbing state. And once you hit that state, you're never coming back, for instance. And so the stationary distribution in that model would have all of its probability mass at the failure state. Right? So it's true. But I think that if the robot's leg falls off when it hits the ground, then your model is no longer valid. And it's, I think absorbing state is sort of a reasonable thing to model it. Better if robot can get back up. But okay, here's another great one. Here's our van der Pol oscillator, right? Our simplest limit cycle, right? You remember the flow for this, where a nominal fixed point or a nominal limit cycle, it'll just move around like this. Points away will converge to it. Points at the origin. There's a fixed point at the origin, but for every other point, it will converge to that limit cycle. So let's say I start a Gaussian blob of initial conditions right there, a bunch of particles. What is the stationary distribution of this system? Nice. Uniformly distributed around the limit cycle, right? It's fun to watch.
Why is it necessarily?
Okay, so it is distributed across the good question, right? So it is, I expect to have probability mass everywhere along the cycle, but I don't mean to say that it's evenly distributed. That's true. In fact, you can kind of tell by the bunchiness that there's places where it kind of slows down and speeds up, and you probably have more. Good. Thank you for calling me out on that. So that one already repeated. It takes a little while to mix, but the stationary distribution looks more like that, yeah. I think it will be distributed across the cycle. It might be uniform in phase, right? But it could have collection points in terms of its total probability mass, right? Just because the magnitude of the derivatives are slightly different in different places, right? If it was a perfect circle, then I would think it'd be uniform, but it's, yes, yeah.
In this case, you started out with uniform distribution?
I just did a Gaussian, I think, but
okay, you did a Gaussian.
Yeah.
And the noise is also?
The noise is Gaussian in this case.
Okay, so you did actually solve this analytically.
For which case?
Well, so both of these are, both of the distributions are Gaussian, so you can actually, so the Gaussian actually remains when you take the integral of the previous.
Good question. So this is a polynomial dynamical system. So even after one step, the Gaussian is no longer Gaussian. In fact, you could see it was elongated, and it could have been an elongated Gaussian, but it wasn't. It was, and this is clearly not Gaussian, right? So, so the nonlinear dynamics makes it so you cannot convolve and stay Gaussians. Great question. And let's just make sure I say this carefully, right? So, why does that spread out intuition make sense, right? Is that we just talked about there's two forces at play. There's one thing that's pushing you out. That's your noise, your disturbances. There's another thing that's pulling you back in. In general, that's the tension in dynamical systems between those two. This system has tension pulling you back in one direction, but there's no stability along the cycle, right? If you were to perturb something along the cycle, there's nothing pushing you back. So you expect it to spread out in the direction that it has no stability, right? The noise wins in that direction, and it's being pushed back in the opposite direction. Yes?
Just by looking at the dynamics, can you say something about whether that's
So that becomes the art of stochastic dynamics, right? So I think you get all of the same, there's analogs of all the same tools, right? But now you have to work on the function space of the probability distributions. For linear systems and Gaussian noise, we know everything. Nonlinear gets arbitrarily complicated, and oftentimes we cannot say anything in a clear way. We can try to find Lyapunov functions. We can try to do all kinds of things. But we're back. I think the analogy to nonlinear, from nonlinear dynamics, linear dynamics to nonlinear dynamics is strong here too. Yep. Yep. So I hear you. So that you could try to account for. I mean, you could write a dynamical system that somehow resets when things get out too far out of bounds and drops the probability back in, or something like this, right? But I think you do need to include those in your dynamics. Otherwise, like if you try to write a robust controller for this that guarantees that the probability stays in some domain, you will fail, because that's going to have no stationary distribution. Right? If you're looking, some RL formulations are, thinking about stationary distributions, and that's not going to do. That solution is not going to have a stationary distribution. Yeah. I think that's right. I think that's right. He's got a Kepler's law analogy, equal segments, equal time, argument for why you expect you could analyze the phase dynamics in that sense. It's not an ellipse, right? So be careful. Yeah. But yeah. I mean, I don't know what we don't have a closed form expression for this, but I do think it would be roughly uniform in phase, apart from the bunching. You'd have to collect that carefully. So probably it's hard to say anything rigorous about it. Yeah. Okay. So those are all smooth dynamics. What happens with contact, right? It's actually super interesting. So what happens if first we need to come up with a probability model that's sort of reasonable for contact. Like adding Gaussian noise doesn't really make sense, because you won't be propelled into intersection with an object, for instance, right? So in fact, the way we write time-stepping algorithms, the way we define discrete time dynamics in our simulators and the like, if we want to, so let's just do the way we often write our solvers, actually, is that we will simulate the unconstrained dynamics forward and then project them back out of contact. This is like a standard way to do this is to actually, let me just do it in a simple example here. So let's say I have just a block of mass m here, okay? And I'll say this thing is Q, okay? So, and let's even say it's unactuated. Of course, it'd be more interesting if it was actuated, but let's just have this thing sort of subject to Brownian motion. But there's a wall there, right? So how are we supposed to write a sort of stochastic dynamics model for an object that's kind of a Brownian motion, but clearly can't go through the wall? That's maybe the fundamental question. And what I was trying to say is that actually the equations that we use to derive contact mechanics in discrete time, there's an interpretation of them where you basically take whatever forces are applied in the unconstrained system with no wall here, you see where the mass would have ended up. And if it ended up in contact, there's a projection that takes it back out of contact. That's what happens in our simulators, in time stepping, okay? And that's what we're going to do here too. We're going to say, I'm going to add Gaussian noise here. But if for the tail of the distribution that ends up in the wall, I'm going to project it back to the wall, okay? So a natural model would be to say I have Qn plus 1 is going to be Q of n plus Wn. I guess I changed notation, sorry. If that's we'll just say the wall's at 0, okay? I'll call that Q equals 0. And otherwise, it's going to be exactly at the wall. So it's like a truncated, it's not quite a truncated Gaussian because the probability mass actually gets projected back to the wall. Okay, so here's my little block on the wall. Okay, the green is kind of what I would do if I just used a Gaussian noise more generally. Okay, but then the pink is going to be, looks like a Gaussian over here. This is this is the one-step dynamics. It looks like a Gaussian over here, but it's got a delta function attached on the wall, which just accumulates all the probability like this. That's a very simple example where the equations work out to be this, but that's actually what's happening in a complicated simulator. If you've got noises or whatever, and you have something that would have gone into penetration, it will get projected back. You're solving with time-stepping LCP or other in Mujoko and Drake and all this, okay? All right, so that's sort of interesting. Now, you could play that out in your head and think about what is the total implications of that. What's the stationary distribution? That's an interesting question. But there's another thing that's sort of really interesting about this, okay? So if I plot the nominal dynamics, so the nominal dynamics here are just nothing. The nominal dynamics would be, if W equals 0, right, then I just have Qn is going to be, Qn plus 1 is just Qn if Qn greater than or equal to 0, okay, and 0 otherwise. That's boring, but it looks like a ReLU, right? The rectified linear, yeah? This one's Qn plus 1, thank you. Good catch, yeah. That looks like a ReLU, okay. But if I plot this one, and I plot the expected value of where I expect to be, so just the mean of this distribution, of this pink distribution, and I change it as a function of Q, okay? So if I look at given my block started here, if I move it left or right, and I plot the expected value of that distribution, then you get this green line here, okay? So what does that mean? So if you're taking a simulator, okay, and you've got randomness inside it, we can talk about where that comes from in a second here, and you are doing computations involving the expected value of the distribution, then contact has this like weird smooth, the noise has a weird smoothing effect with the contact, right? It's as if you're getting contact at a distance on average, and these hard contact events of like being in the wall or not being in the wall are replaced with sort of the smoothed effect that's just smoothed out by randomness, okay? So for instance, when you're doing RL, it's very common to, most RL algorithms will inject a little bit of noise on the outputs of the policy. That's how you do exploration in RL, right? If you take a deterministic simulator for contact and you do RL and inject a little bit of noise, then the interpretation of that is actually that it makes your contact softer. It turns hard contact in probability, if you're going to now optimize the expected value of your rewards or something like this, okay? then it's like it's smoothed out contact. Okay? And even weirder than that, it gives you force at a distance on average. Right? So we talked about in hybrid trajectory optimization, like one of the challenges is that there's no gradient. Like if you're not making contact, there's no gradient that tells you you should go to make contact and pull you back out. But if you're doing stochastic optimization, okay, then contact can actually, you can have signal at a distance. So this is kind of one interpretation of why RL has actually done very well in contact problems, is because some of the simple randomization strategies actually smooth out some of the discontinuities of contact. There's one more too, because if you're doing gradient descent on that, okay, then the gradient descent of the original contact landscape is a nightmare. It looks like a step function, okay, but the expected gradient, looks like this beautiful smooth function. Right? So it's a much better optimization landscape just by having taken that simple model and just played it out. Yes?
Do you get there by actually solving
Sampling is sufficient to get there. In fact, it's very hard to do the closed form expression for any of these. Yeah. So sampling is sufficient to get there. Okay, so that's kind of a fun one. Here's one more to sort of get your intuition going here. So again, contact, okay? You remember the deterministic rimless wheel, right? And you remember we did the analytic return map. So we know that this thing has we did it on video, but it has a fixed point, a rolling fixed point, and a standing fixed point, right? And depending on those, we actually could even solve for where those were given the slope of the ramp and the leg angles and things like this, right? So what happens now if you put a rimless wheel on rough terrain? Okay, this is back when apparently we only had a few pixels. This is the MATLAB render, but okay, rimless wheel rolling on rough terrain. Now it turns out the equations of motion are still beautiful and simple because it's like you basically draw a ramp angle from a distribution and at every step. You can draw as curvy as you want here, but since it's a point foot, it's only going to collide at a certain point, and whatever that point is, that's like a ramp angle that it used the equations of motion that we derived, but it's just now the ramp angle becomes a random variable. Okay? So you can push that back through the equations of motion and ask, like, what are the stochastic dynamics of the rimless wheel? What do you think there? What's the stationary distribution of the rimless wheel? This a bit speaks to your question before about no real system goes to infinity. The video kind of gave it away. It stopped in that rollout, right? There's an absorbing fixed point of this system where the system's standing still. If it's only the ramp angle changing, there's no Gaussian noise pushing or whatever. If I ever get to the standing still fixed point, it's stopped. Right? If I'm rolling, I'll keep rolling with high probability. But on every step, there's some chance that I could pull either one or a series of ramp angles that will eventually cause me to come to a stop. So as time goes to infinity, I know I'm going to be stopped. Okay? But the interesting thing is that it does roll for a long time. And you can ask about the long-living, that balloon that was going slowly losing air. That's interesting. You want to know the shape of that balloon because that's like what the walking robot's going to do for most of its life, right? And back in the MATLAB days, Katie made these amazing animations. Okay, this is the same kind of thing with just it's a slower decaying process, but it does go to the stationary rolling fixed point with high probability. But again, those distributions are going to just very slowly lose mass and run out, okay? And there was a sort of a nice line of work about doing, analyzing the stability of that mode. It's called metastability when you're looking at the long-living transients, the stability of the sort of second eigenvalue of these dynamics. Okay. got these amazing MATLAB skills back in the day. Okay, so this is the deterministic fixed point. Now we do, that's mild rough terrain. Okay, it looks like this. That's the distribution, right? And with some probability it fails, right? But you can actually, in the system, so that was actually, it's a small enough state space that you could discretize everything. You could do everything sort of on a finite Monte Carlo chain and then analyze the first and second modes and get these nice, beautiful solutions. Okay, so we're going to talk next time about control, right? But I think that I wanted you to first just think about all the different things that first just think in terms of probability distributions, how they evolve. And maybe one more philosophical question would be like, do we need this, right? So let's just compare, this is Big Dog back in the day. This is the predecessor of the spot and everything like that in Boston Dynamics, okay? We've talked a lot in class about state stability, right? Deterministic stability. And deterministic stability does give you some kind of robustness. So I want to distinguish here between like rare events, like some jerk came and kicked you, right? And if you'd used only deterministic equations and deterministic control, then after the perturbation, it's like you're in a new initial condition. So being robust to initial conditions in a deterministic sense, having a big ROA, is kind of enough to handle the left-hand side. Right? So everything we do would have worked for that. But the situation's sort of different if the randomness happens at the same time scale as your dynamics, right? If you can't separate out the convergence in stability from the pushing out from randomness, then that's when you really need to sort of integrate the tools of stochastic control. And I think we've seen that, we saw that with sort of these cartoon examples now, but RL has really just shown this incredibly well, right? So nowadays you just see, every day there's like a new video of people throwing quadrupeds and these things just really work, right? And that's largely due to reinforcement learning algorithms optimizing stochastic objectives, right? And very strong light quadrupeds, right? Cool. Oh, I didn't mean to play that again. Okay, so we'll do the control version of it next time. See you then. Yep.